Welcome to the video on the Bohr model of the atom. In this video, we're going to discuss the Bohr model and how we can use the Bohr model to calculate energies, frequencies, and wavelengths for electrons and their either absorbed or emitted radiation as they transition energy levels within the Bohr model. All right, let's start off with what is the Bohr model of the atom. The Bohr model of the atom is a model of the atom in which protons and neutrons are bound in the nucleus and electrons are confined to orbit the atom in discrete energy levels. In other words, they only orbit the electron in various energy levels. They're not free to wander around. They have to be in one of these energy levels as they orbit the atom, as they orbit the nucleus. Well, let's think about where do electrons want to be. Electrons are negatively charged. They would be attracted to a positive nucleus. So electrons want to be in the ground state. So we'll draw a little electron down there in the ground state. In order for an electron to get to a higher energy level, let's talk about energy levels before we continue the discussion here. Over on the right-hand side here, we see in this diagram, which by the way is in your reference table, probably should have that out looking at it while we're having this discussion. The energy levels referred to here are every time you see an energy number over here to the right, for example, down here in the ground state, 13.60 electron volts, or in N equals 2, 3.40 electron volts. What that number means is that's the amount of energy in electron volts required to remove the electron from the atom. So if, for example, this electron was hit by another electron, if that electron had 13.60 electron volts or more energy, it would kick that electron out of the atom, and that electron that was emitted from the atom would have would have what's left over from 13.60 electron volts of energy from the original electron. The other possibility is that the electron gets struck by photons. If that's the case, then the electron, to go to a higher energy level, and this is a very important piece of information, has to absorb the energy from that photon in the exact amount as the energy level transition, or it has to be ionized by the photons to have 13.60 electron volts or more. Okay, for this model being the hydrogen. Physics, or at least the Regents course, really only concentrates on two atoms that we're going to be using here, and that's the hydrogen atom and the mercury atom. Okay. I know this is confusing at first, but we're going to make this pretty simple. So let's see if we can figure out, well, let's suppose we had an electron in the ground state and it got hit by a photon which caused the electron to rise up to the N equals 2 state. How much energy would that photon have to have? Well, it's just stated that energy has to be exactly equal to the energy level difference between the ground state and N equals 2. So that E value is very simple to figure out. You take 13.60 and you subtract the 3.40 that it has in N equals 2, And we take a quick look, and I believe that would be 10.2 electron volts of energy. That means this photon had to have exactly 10.2 electron volts of energy to excite an electron from n equals 1 to n equals 2. Likewise, if our electron now drops back down to the ground state, it would give off a photon with exactly that much energy. E equals 10.2 electron volts. Again, the exact difference between the energy levels. Okay? Now there's some other questions they could ask. They could ask, okay, what is the frequency of the absorbed photon or the frequency of the emitted photon? Before we go into that, this brings up a great point that you must realize that is often tested. When electrons transition up to higher energy levels, the photons are absorbed. So this is a photon that is absorbed. When the electron transitions down to lower energy levels, we say that the photon gets emitted. You must know that. Photons going up absorbs energy from the photons. Electrons that transition down in the diagram emit photons with those energies. Okay? Now what if they asked us, how do you find the frequency of the absorbed or emitted photons? Well, we already know that the relationship between energy and frequency is E equals HF. Another nice thing they could ask you here is, okay, what about the wavelength of the emitted photons? Well, you could find the frequency first and then use the fact that all of them travel the speed of light in the wave equation, or we could simply recognize, oh yeah, we've done this before. Another way to express energy is hc over lambda. Then you could solve for the wavelength, okay, where c is the speed of light. And remember that all members of the electromagnetic spectrum travel the speed of light. Okay, so that's the basics. I'm going to pause for a moment here and clear out this diagram and then share with you some more information. Okay, here we are with a clean hydrogen energy level diagram, as you could find in your reference table. And what I would like to take a look at here is 4 emitted photons in the hydrogen atom that are visible to the human eye. There's only 4. Okay? And they are when an electron transitions from n equals 6 to n equals 2, n equals 5 to n equals 2, n equals 4 to n equals 2, and n equals 3 to n equals 2. Well, we understand that the energy of those 4 emissions will be given by E equals HF or E equals HC over lambda. So what if I told you that one of those transitions produced a photon visible to our eye that was red? Which one would that be? Well, if you go to page 2 of the reference table and you look at the comparison of the colors in the color spectrum, you notice that the colors are broken up and categorized according to frequency. The red has a lower frequency than the violet. And the resulting energy then that would be required here would also be decreased. So the lowest frequency color emitted would require the least energy jump. Which one would that be? Well, if you said 3 to 2, you would be correct. So the jump from 3 to 2 emits a red photon. The jump from 4 to 2 emits a nice teal blue-green photon. The jump from 5 to 2 emits a blue-violet photon. And the jump from 6 to 2 emits a very dark violet photon, one that's actually barely visible by the human eye. So those colors, once again, are red, blue-green, blue-violet, and violet. These four colors make up, these four emitted photons make up what is called the Balmer series of the hydrogen energy spectrum. And they are the only four visible wavelengths of light given off during energy transitions by electrons in the hydrogen atom. Not only that, we could take a look at the fact that this is if the electrons drop down to the n equals 2 state. What if they went from n equals 2 to n equals 3, or from 2 to 4, or 2 to 5, or 2 to 6? Then what would happen is those electrons would absorb those same wavelengths. And what we get, and you may have seen this before, is the absorption spectrum and the emission spectrum for hydrogen. You note that for the absorption spectrum, it's the continuous color spectrum that is simply missing the four exact wavelengths that are absorbed by the hydrogen atom during the transitions from 2 up to 3, 4, 5, and 6. In the hydrogen emission spectrum, it's totally black except for the four spectral lines that we see for the hydrogen atom. So this will conclude our notes on the Bohr model of the atom. We'll have much more practice with this in the problems that you do in the problem set.